going back to graphs of rational functions in this video. This is picking up where the last video left off with two different types of rational functions to graph, and then we'll finish it with an application problem involving a rational function. Notice that in this first equation here, h of x is equal to negative 5x all over x squared minus 9, that x squared minus 9 factors to x minus 3 times x plus 3. So that looks like I have two vertical asymptotes. I have x equals 3 and I have x equals negative 3. I don't know if you can see that very well. It looks like it's appearing on the screen. I have one horizontal asymptote because the degree of the numerator is smaller than the degree of the denominator. So I have as a horizontal asymptote y equals 0, the x-axis. Now, I don't know how much you guys are thinking about symmetry when you have a graph like this, but this is actually, it's going to show that it does have symmetry here to the origin. If you take h of the opposite of x, so that would be negative 5 times the opposite of x all over the opposite of x squared minus 9, which is 5x all over x squared minus 9, because the opposite of x squared, hopefully you can still see that, it's kind of small, which would be the opposite of negative 5x all over x squared minus 9, which would be the opposite of h of x. Well, if h of the opposite of x is equal to opposite of h of x, then we have symmetry to the origin. This is an odd function. Now those alone are getting you going here, and I'm going to go ahead and put my draw my asymptotes in here in just a minute. But I will also consider some possible looking for possible intercepts. For example, if you plug 0 in for x, you get 0. So I have as an x-intercept, excuse me, as a y-intercept, I have 0, 0. Well, not only is 0, 0 a y-intercept, it's also an x-intercept. And in this case, I believe it's the only intercept that I have. So, I mean, you could go ahead and make y equal to 0 and solve for x, but I believe you're only going to get 0 here. So those are all good things to have, but when you have a graph that you've not done before, all this information is good, but you're definitely going to want a t-chart with x and y. I didn't leave a lot of space, and I'll pick some points here in just a second and plug in some values. But first things first, let's put these asymptotes in. So I have x equals 3 and x equals negative 3. Alright, so 1, 2, 3. I'm going to use this to make it a little bit nicer. Again, you're using graph paper, so you should have and a straight edge, and you should have good graphs. Not sloppy like mine. Something you can be proud of turning in. And x equals positive 3. And what you'll see here is that your plane is going to be divvied up into a bunch of regions. So x equals negative 3, x equals positive 3, and then of course y equals 0, that's the x-axis. I'll try to put the marks here so you can see it a little bit. Oh, maybe not. Yeah, sliding. There we go. And let's see here. I kind of erased one of my marks. I need that. Alright. Now, here, and of course we have the origin. But that's the only point we have. And my suggestion is that we're going to have our graph kind of like in three parts. We'll have something here in the middle, and we'll have something either above and below, or below, and over here above or below. So I'm going to need to plug some points in. Now I would suggest you make up a healthy size t-chart here with enough points. I've got, I think, about 12 or 13 here that I've done when I was working this out before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, I'll add more if I need it. And I have negative 5, negative 4, negative 3.5, because I'm getting closer to the vertical asymptote, negative 2.5, negative 2, negative 1, 0, I already know 0, 0, 0, 1, 2, 2.5, 3.5, 4, and then one more here, 5. Now, here's the good news. You don't have to plug all of these points in, because we know that h of the opposite of x is equal to opposite of h of x. So if we use that symmetry, what happens here at -5 is going to be the opposite here at +5. And so if you start plugging these numbers in, and it's a pain because you get a lot of fractions. You get 25/16, you get 27ths, you get 70/13, you get -50/11ths, you get -2, you get -5/8, and then the rest of them, you see how the signs will change. This would become +5/8, this would be a +2, this would be 50/11ths, this will be 70/13, this will be 27ths, and this will be 25/16. Now, I picked these points equally distant from the origin so that I could use the symmetry and not have to spend forever plugging in values. So I'm going to graph from here to here, and then I'm going to use that pattern that I have to figure out exactly what's going on to the right of the origin. So let's plot some points now. -5, this is -3, -4, -5. Uh-oh, I put it right smack dab on here, is at 25/16, which is about 1.5 approximately. So it'd be about here. I hope I can make that dot big enough. -4/27, this is not quite 3. -4, not quite 3, be about here. -3.5, this is 70/13, which is 5 and some change, about 5 1/3, 5 1/2. So let's see, that was 3, 4, 5 1/2. I'm going to approximate it here. And you see how the curve is beginning. And you know that we have a horizontal asymptote here and a vertical asymptote here. We would want to plug in maybe a few more points in, but we can start to determine our branch here, our part of the graph. So what we have here is going to be also over here. It's just going to be like rotated 180 degrees to come over here. But I'm going to continue. -2.5, -50/11, that would be about -4.5. So -2.5, 4.5 approximately here. -2, -2, that's kind of nice. -1, -5/8, spot here. 0, 0. Do you see what I have here for the curve? Now again, I've graphed a few of these so I can kind of see the patterns coming. When you're doing these for the first time, plot as many points as you think you'll need. Now, if I use the fact that I have symmetry here, I really don't even need all these points. I could graph them, and I will, to help me with it, but I kind of know that this is spun around here. It's going to go up like this. But I'll go ahead and graph 1, 5/8, 2, 2, 2.5, about 4.5. 1, 2, 3, 4, and about like this. And so you can see it's going to go up like that. And then I have, let's see here. Oh, hang on a second. Did I not change the signs? I did not change the signs. I was going to say, I don't think it's up there. These are all negative because these were all positive. I apologize. Let's see, do I have everything else right? I think I have everything else right. Sorry about that. So this is going to be -70/13, which again is about -6 1/3. No, hang on. About -5 1/3, 5 1/2. So let's see. 1, 2, 3, 4, 5, about down here. Let's see what else we have. We have 4, about not quite -3. And we have 5, about -1.5, give or take. So we have that part of the graph as well. Now don't expect to do these graphs in 25 seconds, especially when you're doing these for the first time. And it's a little sloppy, but you'll do a neater job on graph paper. Plot those points, use intercepts, asymptotes, symmetry when possible to help you with the graph. Alright, now I haven't done one with an oblique asymptote. I've got that one coming this way. I'm going to graph k of x is equal to 2x squared minus 7x plus 3 all over x minus 2. Well, I can see right away that I have a vertical asymptote. Let's see where I can put all this information. I have a vertical asymptote at x equals 2. I do not have a horizontal asymptote, but because the degree of the numerator is 1 greater than the degree of the denominator, I do have an oblique or slant asymptote, and I need to find that. Okay, so that's going to give me 2x minus 3. I have a slant asymptote at y equals 2x minus 3. 2x minus 3. That's the remainder. That's not part of it. So that's going to help me. I'm going to graph those here in just a minute. And then what kind of intercepts do I have? Well, if I plug 0 in, I have a y-intercept of, let's see, if I plug 0 in, I get 3 over negative 2, so I have 0, negative 3 halves. And my x-intercepts, let's see if I have an x-intercept. So I set this equal to 0, this equals 0 if the numerator is 0. So I set 2x squared minus 7x plus 3 equal to 0. Let's see, does it factor? I think maybe it might. If I put a minus 3 here and a minus 1 here, so that's going to give me x equal 1/2 and 3. So I'm going to have x-intercepts of 1/2 0 and 3 0. Oh, don't need this. Not sure why I put that parenthesis there. You can check for symmetry, but I'm pretty sure I've done this one before, and I don't think this is symmetric to the origin or to the y-axis. Of course, it won't be symmetric to the x-axis because it's a function. Now, that's a good start, and I'll get my handy-dandy yardstick here. And it is a yardstick, it is not a meter stick. So let's see what happens here. We have a vertical asymptote at x equals 2. So I'll draw that in. X equals 2. And then I have a slant asymptote. This line y equals 2x minus 3. So that means it has a y-intercept of negative 3 and the slope is 2. See if I can draw this one without letting the yardstick slide. Okay, so do you see the 4 regions? You've got these 2 narrow regions and then these 2 much wider regions. So more than likely your graph is going to be in 2 of those regions, and we'll see which 2 here in just a second. We definitely have some points that we can graph. We have 1/2 0, 3 0. Looks like it's going to be in these 2 regions, these 2 wider regions. And we also have 0, negative 3 halves, which is negative 1.5. Well, that's not enough points. I mean, I know some students will try to go generalize here and make very wide sweeping branches using the asymptotes. But here again, my suggestion would be to plug in some values. So, create a table. And in this case, I would probably use, well, everything's happening around 2. I might go as far back as negative 3 and 1.5, and then 2.5, 3, 4, 5, 6, I don't know if I'll need to go as far as 7, and plug those in. Now, this is really the time-consuming part, is plugging these values in, especially with the fractions. But I went ahead and did it before class here, and before my video, I should say. Negative 25 fourths, negative 4, well, we should know this one is negative 3 halves, 0, negative 3 halves, 1, 2, 1.56, 2.5, negative 4, and 0, we should have 3, 0, there we do, 4, 7 halves, 3.5, 6, 33 fourths, and yeah, this one's going to be too much. This is going to be 52 tenths, or 52 fifths, I should say. And I think I'm off my sketch there by then. But now I can sketch these points to help me out. Negative 3. Here, let's use a different color here. Let's make these points in black here so we can see them. Now let's make the rest of the sketch here in black so it complements the asymptotes there. So -3, this is -8 2/5. -3, -1, 2, 3, 4, 5, 6, 7, 8. It'd be all the way down here. Okay, well, it's so far down there that it's not matching up with my poorly drawn one there. So 1, 2, 3, 4, 5. Yeah, I made this too long here. Got to use graph paper, but it'd be way down here. Practically on the asymptote, but not. -2, well, that'd be about -6 1/4. Be way down here as well. -1, -4. 0, I've got that. I've got 1, 2, 1.5, 3, 4, 5, 6, and I think that's going to have to do it. So here we go. Does not cross this asymptote. My hand slipped. Oh, that is not so good. I hope you have a steadier hand than I do. Let's graph the other side here. We have 2.5, -4. Let's see, 2.5, -1, 2, 3, 4. 3, 0 I have, 4, 1.5, 5, 6. 5, I don't know if my sketch is good enough to do this one. 1, 2, 3, 4, 5, 6. Ah, looks like it's going to be off a little bit. And, well, that's not going to make it any better because that's way going to be off the sketch. So, and I wish I could say that somebody else had drawn that, but this is my work, and there we got it. And that is going to challenge you to take your time, to be neat, to use graph paper, to use a straight edge as you're graphing this out. Fortunately, the last example does not involve me graphing, which is good because those aren't so good looking. Power company burns coal to generate electricity. The cost C of X in thousands of dollars to remove X% of the air pollutants is given by C of X is equal to 600X over 100 minus X. All right, remember X is the percent of the air pollutants that are removed. Compute the cost to remove 25% of the air pollutants. Well, that's just another way of saying, with that function, 5C of 25. So that's 600 times 25 all over 100 minus 25. Well, 6 times 25 is 150, so this would be 150 with 2 zeros, and this would be 75. Well, 75 goes in 152 times, so that's going to be 200. Now remember, C of X is in thousands of dollars, so to remove 25% of the air pollutants, the company, the cost will be, let's say that, the cost will be, this is in thousands of dollars, so this would be $200,000. Okay? Now, in part B, it says if the power company budgets $1.4 million for pollution control, what percent of the air pollution can be removed? Well, in this case, 1.4 million, we got to think of this in terms of thousands. 1.4 million is 1,400 thousandths. Don't plug 1.4 million in for this problem because it's not going to work out. Remember, C of X is in thousands of dollars. So I'm going to plug 1,400 in for C of X right here. And I have 1,400 is equal to 600X all over 100 minus X. If you'd like, put it over 1 and cross multiply. I get 600X is equal to 1,400 times the quantity 100 minus X. I get 600X is equal to 1,40000 minus 1,400X. Let's put a comma in there. I'm going to add 1400x to both sides, and I'm too lazy to write it out. I guess I'm not that lazy. I've already got committed it this way. And these cancel out. I get 2000 x is equal to 140,000. Divide both sides by 2,000. And I get 70. Now what's x? X is the percent of the air pollutants removed. X is 70. We're looking at 70%. What percent of the air pollution can be removed? 70% of the air pollution can be removed if $1.4 million are spent. 1.4 million, let's do it this way, are spent. And that's the answer to that problem, and that is the end of this section.